Hello there, welcome to this video. In this video, we're going to look at another way to combine probability distributions with the QPython package. This time, instead of acting directly on random variables, we're going to do something that acts on the probability distributions for those variables. So suppose we have an amount of time that it takes to complete a service, and maybe let's say that it has two components. We've got maybe T1, and some of the time it takes a gamma distribution amount of time with parameters 1 and 2. But some of the time, maybe it follows a different distribution of gamma, something maybe substantially different, like 10-2. We don't know exactly when a given sampling is from T1 versus T2, but perhaps we know that there is some probability of observing something from T2 versus T1, calling that probability P perhaps. So that's what we're going to look in this in this video, is how to construct distributions where we're not explicitly labeling the data by these different subpopulations, but we do want to be able to sample from subpopulations that we haven't directly labeled. Okay, so let's go import Q, and we're going to define a distribution. And in this case, we're going to use Q has explicit support for something called a mixture distribution, and it takes a couple of different parameters. One of them is that we have to give it some probabilities, and we also have to give it some probability distributions. So if I remember the ordering right, or can I just look it up there? No, it doesn't show right now. Might need to update some doc strings. So q.dists, and we will add that. Let's just go with the example we started with. So a gamma 1, 2, and then also q.dists gamma 10, 2. And then for the probabilities, let's say that 0.75% of the time we see the gamma 1, 2 distribution, and then the rest of the time we see the gamma 10, 2 distribution. So we've defined this compound distribution. The individual distributions within the model are called components, or at least they're often called components of a mixture. And these are the weights. They're often called weights. They have to add up to 1, and they're no greater than 1 individually, and they're non-negative, so they're basically probabilities of observing one of these subpopulations. So this, like any other distribution in the QPython package, you can sample from it by just calling sample. So there's a sample from this distribution. Looking at that 0.62, I actually don't know which of the subpopulations it came from. And that's kind of the point with mixtures, is to say that you know that there's substructure to the population, but you don't know on any given sampling which one it came from. So let's make a plot just to get a sense of what these distributions look like together. So let's grab matplotlib.pyplot as plt. And let's hop down to the bottom here and create a bunch of samples. We'll call dist.sample for underscore in range, and let's say 10,000 for a sample size. Why not? And we'll go plt.hist and pass in our samples, and then we'll assign 100 bins. I find often does the trick, though it does depend on some details. But anyway, this should work pretty well. Let's take a look. So you can see that there's a bit more of a, it's not quite, you know, an idealized bimodal normal distribution type of thing, because the left-hand region there looks like something closer to, you know, an exponential. Technically, it's a gamma, right? And technically, both of these are gamma. But you can see there's this kind of bulge here that has a tail that goes off, and that's probably our second component. Now, just to get a sense of what we just did there, let's maybe also break our example down into the components. So we had the q.dists.gamma 1, 2, and then we had the second component is 10. And we could probably leave that there, but let's just use the same components. So if I say that these are, yeah, it's probably fine for me to just leave this as samples, but I'm going to need samples. We'll call this samples 1. And what I'm going to do here is sample from component 1, and then also do the same with component 2. Because what I'd like to show, if I may, is just to superimpose the component samples. Yeah, so we can say samples 1 and 2. Probably add some labels. Just call it comp 1. So there we can see the components a bit more clearly. However, we're still blocking view of our mixture in the background. So to help with that, let's also add an alpha of point. Well, we don't need any alpha on the original samples. Sorry, the mixtures. But on the components, yeah, let's add an alpha level here, just so we don't drown out the mixture in the background. And let's also, just for clarity, show the legend. There, that's a little bit more clear, I think. Let's blow that up a bit. And so you can see that the mixture kind of represents a combination of the two, right? I mean, they're not exactly the same, because in this case, and especially in this case, our mixture weights are not the same. So we had mixture weights of, 0.75 as well as 0.25. So it's not a balanced mixture. That's one of the things that mixtures allow you to do, is to say, well, you're not seeing each of the subpopulations with equal probability. There are different probabilities for different subpopulations for whether you see them in the first place. Hopefully you find that helpful. That is one of the useful tricks when you need to model something that you can't directly label in the data. And when you do have labels, perhaps we'll make another custom distribution another time. Let me know in the comments if that's something you'd like, of how to deal with when you do have labels. But for this case, I'm going to close out, and hopefully you find that useful, and I will catch you in the next video. Have a great day.